complex which is of dimension d, and therefore it has d plus 1 points, face f, tau restricted to f is 1 to 1, and therefore also on 2, right? Because tau, so assume I have such a coloring. Okay, now, and maybe when I already defined it, but when I define it, it looks a little bit artificial, but now you remember that there was a very natural example, the spherical, the flag complex, the complex of all the subspaces of a vector space. In that flag complex, we had the type function was the dimension, the vertices were all the subspaces without 0 in the full space, and the type was the dimension, right? The only difference there that we really took it to 1 up to d minus 1 or something like that instead of 0, but that doesn't matter, of course. And I want to assume also, and that's important for us today, assume that x tau is regular. So here I want to, again, to remind what I mean by that, because this looks, I mean, I already defined it, but I think before the example it looked a little bit artificial, and now you understand why we're doing this like that. If for every I inside J, inside the type function 0 up to d, I take, you see, in a natural way, if I have a coloring of the vertices, I have well, I don't want to call it coloring. I can call it coloring, but there is kind of a reason why I don't want to call it coloring. I prefer to call it type. But if I have such a type function on the vertices, then naturally I have also a type function on each face. Each face, the type of it is the subset of the types of its vertices, right? And then I wanted for every I and j, the number for every face f of type I, so which means i.e. tau of the set f is equal exactly I, the number of faces of type, of type J containing it is k I j. It's not important for me what's the number, but I want to say i.e. depends only on I and j, but not on f. Okay? This is the long definition that I gave also before the example, but it may look artificial. Think about graphs. Then, do you know what is a graph? Graph is a regular graph. Is a graph, so the degree of every vertex is the same. You would think that the natural generalization of a regular would be that say that for every edge, the number of triangles containing the edge is constant. But not quite. I mean, okay, that's also possible, of course, but there are many natural examples, and the examples that of the flagged manifolds are exactly like that, that without the coloring, they are not regular. Let me just recall, I gave you, I started with this, but then we went to other things. If you look at the flagged function, the spherical function, I think, of dimension 4, I think this is the first time that you start to see it, then you see what are the edges here. Or even what are the vertices here. You see, the vertices here are are those of dimension 1, those of dimension 2, and those of dimension 3. And if you ask yourself how many edges you have around what is an edge now? The vertices are exactly the subspaces. The edges are flag of size 2. And the maximal faces are triangles, the flags of size 3. So if you take a vertex here and you ask yourself, what's the degree of it as a vertex? Then this is the number of things going from ear to ear, as well as the number of things going from ear to ear. And we saw that this is the same from each one ear. It's actually the same from each one ear also, but it's a different one for dimension 2. And again, if you will look even on edges, take this edge and ask how many flags you have containing this, with edges here we still with edges, all the edges are inside Q plus 1 triangles. So the degree, the edge degree here is still the same. But if you will go to S5Q, go one dimension higher, and then we have dimension 1, dimension 2, dimension 3, and dimension 4. And then think about it and calculate it. If you take say an edge, which is, what is an edge? Is a pair of two subspaces, one of dimension 1 of one of dimension 2, so that this one is inside this one, right? And you will ask yourself how many triangles you have containing it. Well, so you can complete it to a triangle in two different ways. You can choose a subspace of dimension 3 containing it, or a subspace of dimension 4. And you can calculate what's the number. This is not so difficult. It's going to be, I think, twice q squared plus q plus 1. Think about that. On the other hand, if your edge is something which go all the way from 1 to 3, this is also an edge. Okay? And now you want to continue this, to extend this to a triangle, which means that you have a flag of length 2, and you want to enlarge it, to extend it to a flag of length 3, then you can choose either a subspace of dimension 2 between the two of them, and then you have q plus 1 possibilities, or to choose a subspace between 3 and the full space 5, and then you have again q plus 1. So the number will be only 2q plus 1. So you see that edges of the first type are inside this amount of triangles, and edges of the second type are under this amount of triangles. So it's not the same thing. You know, you have to be careful. But once we give the numbers, we give the coloring that this is the same. So maybe, I mean, it's easy to prove it, but maybe let me give you as an exercise, just to convince yourself that S and Q are regular with respect to so here I have to say what is the type function with respect to the type function, which is the natural one, sending a subspace to its dimension. Well, if you want to be very, very formal, because we want it to go from 0 up to something, then it should send it to dimension -1. But of course it doesn't matter, these are just names. Okay. So what I want to do today, I want to define and estimate the discrepancy of a simplicial complex, which is something very important for us in the future. And this is the following. So definition, or maybe let's continue with, to set notation. Notation denote vi will be tau to the minus 1 of I. So these are all the vertices of type I. Okay? Of color I. And the definition is let A, we don't even need to be all of them. We can say let AI1 up to AI2, AIT, we'll say I1, I2, IT is a subset of 0 up to D. Such that Aij is a subset of Bj. So I'm taking T colors, T types, and I want to evaluate how many
Vij.
what?
Vij.
Vij. Thank you. And I want to evaluate the node E of AI1 up to AIT. This is the, maybe let's call this I. This is the faces of type I. I want to count the faces of type I whose points are, whose vertices are in Aij union of them. Well, it's clearly, if it's the case, clearly one vertex. So exactly, that's automatic. Exactly one vertex in each Aij. I'm taking the faces so that the legs of the face, namely the vertices of them, are inside these specific subsets in Vij. Okay, and denote Xi. This is the set of all faces of type I. And I want to evaluate and then define the discrepancy with respect to X, and if we are precisely, it's X and tau, of the set AI1 up to AIT. The discrepancy is defined as the size of EAI1 up to AIT divided by the size of XI minus the product J goes from 1 up to T of the size of Aij divided by the size of Bij. It's something very, very intuitive, very clear. Just to write it down, it takes a long time. But it's very clear. What I'm saying here, I look at all the faces of type I. Right? What is the faces of type I? These are the faces which have a unique vertex in each one of the Vij. Because I is the set, I1 up to IT is the set of colors. So I want to look, say, only on the triangles of colors blue, red, and yellow. only of these colors. But among them, I want to ask how many of them the blue vertex is from a specific type, is inside Aij. And the red one is of a specific type, and the yellow one is of a specific type. What is the proportion? Now, what is the expected value? If there would be just in the world, and everything would be kind of distributed randomly between the sets, then this is exactly the right proportion. The right proportion that I have to take, the proportion of Aij inside Bij. Right? If I take half of the blue, half of the red, and half of the yellow, then I expect that approximately 1/8 of the triangles will be and exactly this half, exactly this half, and exactly this half, right? This is the kind of the expected value.
So this is like entropy or something?
What?
This is like entropy or something?
No, this is because of edges. Like, I mean, it's kind of,
It reminds the Whitney Loomis stuff.
the what?
Whitney Loomis.
What is Whitney Loomis?
I'll show you later. It's in Noga's book.
What?
It's in Noga's book. I'll show you later.
Maybe.
It's very much.
I mean, we'll see. This is something for an extension from graph to hypergraph. We can talk about hypergraph. So this is the edges. I mean, the language. I prefer the language of simplicial complex, but somehow, I mean, we could do all this in the language of hypergraphs if you prefer. Maybe I'll say something about it at some point, but I don't want to start now. Okay, so this is the definition of the discrepancy of a set. So what's the truth with respect to the expected? What's the difference between them? And we usually interested in this, if we are most interested, and we will see in a minute that in some sense everything boils down to that case under the assumption of regularity, in the case where I is everything. So I want to have this. So in particular, we look if I is everything, all the colors, I'm going to define the following. I will define the discrepancy. Now maybe I'll just write it. Discrepancy with capital D. Discrepancy of X star. The discrepancy of the complex will be just one number. And it will be the following. It will be the maximum over all possibilities of AI1, A0, A1 up to AD, such that AI is inside VI. I look at all the possibilities of choosing sets of sets AI inside VI, and then I will look at the discrepancy X star of these sets A0 up to A D. What's the proportion? What's the distance between these proportions and the expected value? And I take maximum over all possible subsets. Okay, this will be the discrepancy of the simplicial complex. So it's one number. If this number is very, very small, then it really means that it behaves like a random complex. Because it really means that whenever you pick up subsets, then the number of edges, the number of faces, in this case maximal faces, but in a minute we'll see that under the regularity assumption, it really gives you much more information. Then it behaves like more or less, if it would be 0, kind of an ideal situation, then it really means that always it's exactly this number. It's exactly what should be, it is. That's what I have. I will call your attention in a minute to show you that extenders are exactly the kind of graphs such that their discrepancy is small, is very small. It's equivalent. So in some sense, this is another kind of definition of expander in a higher dimensional case. And in many ways, my main goal in this semester is to show you explicit constructions of high-dimensional expanders in this sense. Namely, simplicial complexes will satisfy such a strong condition. That's a very strong condition, and it's an highly non-trivial construction. I mean, it's not going to be easy. We're going to go through a presentation theory and through quite a lot of stuff in order to get it. And so this is kind of a crucial, the definition is not difficult. But let me recall, maybe we recall first something that we really saw it for bipartite graph. You see, let's look at the bipartite graph. Bipartite graph is a special case of, I want to recall and I want to I don't remember if I spoke, I probably had to speak at that time, but then I'm not sure that if I really define it in this way. But recall that if B is a bipartite, biregular, so let's say K1, K2, biregular graph. Okay. Then what does it mean? I have two sides. I have here degree 4, say, and here I have degree 3. So here I have K1 degrees K1, and here K2. Now this is a simplicial complex. Every graph is a simplicial complex. It's a simplicial complex with two colors. This is color 0, say, and this is color 1. It's regular. It is regular in the sense of simplicial complexes. It's regular, not biregular. With the coloring, it's regular, because let's think about it. What does it mean to be regular with the coloring? To be regular with the coloring, it means that for every color, I and J, set of colors, I and J, so there are only two possibilities. For I, well, I can take I to be, say, 0, and J to be 0 and 1. Or I can take 1 and 1 and 0 and J to be 0, 1, right? Are you with me? Then the number of vertices of type 0 inside edges of type 0, 1 is exactly K1. And the number of vertices, and given a vertex of type 1, the number of edges of type 0, 1 containing it is exactly K2. So this is a simplicial, so this is B with the function tau, which sends you the vertices to 0, 1, is a regular, pure simplicial complex in our notations, in our definitions of today. I mean, I think of it as a biregular when I talk about graph, because it's really biregular, but it's really regular with the coloring. Is it clear? I mean, it's a trivial point, but let me clear. Okay, now let me ask you, because one of the disadvantages of this course, I have to admit, that I'm kind of preparing the course along teaching it. It's not like I had the full course prepared in advance. So I formulated something about discrepancy in one of the classes, but I'm not sure if I formulated it in a exactly the way I need it now. Remember I told you if you take a subset A here and a subset B here, then we computed EAB and we divided it, I think, by all the number of edges, right? Or something like that. That's what we did, or what did we write? Or I had the lemma, which I proved. Or maybe I gave it and Uriah did it. I'm not sure now. I don't have. Do you have some notes? You remember I take a biregular graph and I call it the mixing lemma. There was a mixing lemma. Can you just tell me what was the mixing lemma?
It was exactly the same as
EAB, I divided by E, or I wrote something, what was the?
divided by E,
Yeah,
subtracted AB
yeah,
over D1, D2.
over what? Ah, okay, this, that's what I did?
Wait a sec. Yeah.
Yeah, and then we said that this is less than?
Lambda times square root of A over E
Lambda of B, which is the second largest eigenvalue,
times square root of A over E
times square root of A,
times square root of B over E.
what was?
So you got started from, so this was the original formulation, then you reformulated.
I formulated it like here, okay. So, yeah, okay. So this divided by E, this divided by B divided by E, that's what I did.
What's the lambda of B?
Second largest eigenvalue.
Okay. No, and right after that, I said, I will say myself, okay. And right after that, I said that this is lambda B, which is the second largest eigenvalue. I took this out, it's the next one, divided by K1, K2, times square root of A over V, 1, times B over V2, right? That's this. That's okay. So now think about it in the terminology of today. I really had to define already their discrepancy. And really what I showed you there is that, you see, this is exactly the discrepancy. This is the discrepancy of the two subsets A and B. This is like today, A1, A0 and A1, right? And I ask how many edges from A0 to A1 divide by the total number of edges. And this is the right proportion. And this is bounded by this ratio, which is, let me remind you, this is the second eigenvalue divided by the first eigenvalue. Remember? We showed that this is the first eigenvalue of the first eigenvalue of the bipartite graph. Now this is a square root of numbers which is less than 1. So it's also less than 1. So we can even give up on this one and we can say that this is at most lambda b divided by square root of k1, k2. So if we will define, let's define lambda normalized of b to be, you remember in a k-regular graph, sometimes we want to normalize and we take and we divide all the eigenvalues by the largest one, by k. If we define lambda normalized of b as what we called before, lambda of b divided by square root of k1, k2, then really what we proved here, that the discrepancy of b with respect to this term function is at most the lambda normalized of b. That's really what, or it follows from what we proved for the graph. And now I want to show you a way to estimate the discrepancy of the full simplicial complex. So the way we'll do it, we'll do the following. Is the theorem of composition.
It's that discrepancy denoted with a,
What?
with a capital D.
This is now capital. That's maybe the way we should think about that. And then I will do the following. Proposition. Well, okay. Let x tau as before, with all the good assumptions, pure, regular, etc. Let bi yeah, I prefer maybe to define something. Let's give the general definition that we need in the proof before that it will save time. For I and j disjoint this time. It's not necessary, but more convenient. Disjoint, and both of them subsets of 0 up to d. I will define the graph bij. This will be a bipartite graph. I have a simplicial complex, I-dimensional simplicial complex. I'm defining a bipartite graph out of it in the following way. To define a bipartite graph, I have to tell you who is in one side, who is in the other side, and when I put an edge between them. Bij it will be xi on one side, xj on the other side. You remember what is xi and xj? Xi are all the faces of type I. Xj are all the faces of type j. And the edges E will be that f1 in xi and f2 in xj are connected if and only if are connected by an edge, if and only if simply f1 union f2 is in xi union j. If the union of them is a face, okay. I mean, maybe it's not a face. I can take several vertices here, I can take a triangle here and an edge here. If together they give me a face, then I put a line in this bipartite graph. So this is a bipartite graph. And spatial case, which will denote bi, is, formally speaking, is the set I and the set 0 up to d minus I. I will look at the bipartite graph such that on one side I have all the vertices of type I. So this is, if you want to be very explicit, is Wi with walls, I will call it without I, and edges. So what does it mean? On one side I have all the vertices of type I, and on the other side I have all the faces which are of codimension 1, and they have all the colors except of I. Okay? Things like that we call walls, right? We have chambers, kind of our nickname for maximal faces is chamber, and codimension 1 we'll call them walls, right? We have to think about it like we have galleries. You remember we have galleries, we have rooms, and the walls between them. So this is, you take the vertices of type I and the walls without I, and you define an edge between a vertex of type I, a wall without I, if and only if together they give you a chamber. Okay? Let's say that we are in dimension 2, so this is a graph. One side are all the blue vertices, and the other side are all the walls of color red and yellow, and we put an edge if together they form a triangle. Very simple. This is a bipartite graph. And now I'm ready to write the proposition. The proposition, which is very important for us somehow, to evaluate the discrepancy of the x, so x tau as before. Then the discrepancy of x tau, which is what we defined before, is at most sigma lambda normalized of these BIs. Or if you want, this is at most d plus 1 times the maximum of them. Usually that's enough. You remember we evaluated, we remember that we defined for a bipartite graph, the second largest eigenvalue normalized is really the second largest eigenvalue divided by square root of k1, k2, which are the degrees. So usually this is something which is very easy, or well, I don't want to say it's so easy, but sometimes it will be easy to evaluate the eigenvalues of this bipartite graph. Maybe not so easy. I showed you some examples about various examples of bipartite graph that we somehow, usually the technique is we spend some time on this technique, and sometimes it's not so trivial, but if we can evaluate the eigenvalues of the bipartite graph of one color against all the others, then, which are really, I mean, in a way, you'll see the proof will give us even more than that. The proof really will bound the discrepancy of the full simplicial complex in terms of the discrepancy of this bipartite graph. So I'm looking at this bipartite graph of one color against all the other. So I have D plus 1 bipartite graphs like that, and the eigenvalues of them will bound the discrepancy. Our goal will, as I mentioned to you, will eventually be to show that there are d-dimensional simplicial complexes with a very small discrepancy, because they will behave like expanders, they will behave like random simplicial complexes, and we understand that that's kind of an important for various applications. And the key will be to show that these bipartite graphs behave like random, are good expanders. Are good expanders as bipartite graphs. So this is really what we want to do. Let me even take, I know that's time for the break, but let me take just 2-3 minutes. I want to write the main lemma in proving this, and then, after the break, we will prove the proposition. Or maybe I will, maybe I will write kind of a lemma 0 even before the main lemma, which if we understand this lemma, then I think the proof later on won't be that difficult. Lemma 0, which is really just corollary of the notation, is that the description. So if I take, say, I'll do it for one of them, but it's the same thing. If we take, say, you will see, it will be clear to you. If I take, say, A0 to be the full set, V0. I'm taking, for A0, I'm taking all the vertices of type 0. And then I want to evaluate what is the discrepancy in X tau, the V0, and then I have A1 up to AB. These are some subsets, right? AI are inside VI, but for the first one, I take everything. And then I take, for the second one, I take A1 up to AD. I claim that this is the same as the discrepancy as we defined before for A1 up to AD without the first set. If I allow to take in the first set everything, then it doesn't matter. There's no influence. Why? The proof is, what is this? This is the number, by definition, this is the number of vertices, of the number of faces of type A0, which lies on A0 up to AD, divided by the total number of all maximum faces, right? In this case is the number of all faces, so this really means E of, let's write it like that, V0, V1 up to Vd, right? This is the way to write all the maximum faces. Minus the product I goes from 0 up to D of V0, this is 1. Maybe I'll write it like that. It's A0 divided by V0, but this is equal to 1. A1 divided by V1, etc. Up to AD divided by VD. Right? But this is 1. Right? Because I took everything. So, and here the point is the following. Now I'm using the regularity. Because what is this? This is equal, I'm claiming that this is equal to what we called before K of the full set. Okay, let's call D the set 0 up to D. Everything, all the colors, all the types. So you remember I said that the complex is regular, which means that if I take a face of type 1, 2, 3 up to D, and then I want to say take such a face, and then I allow you to take the others and take the pyramid, you know, the chambers, so that the color 0, you can take everything. right? So you remember that we said that this is depending only on the two sets. So it's depending only on the set 1 up to D. So the set D minus 0 inside the full D, which is some constant, time E of A1 up to AD, which is the number of faces of type 1 up to D without 0, right? Because each one of them is contained in some fixed number of maximal chambers, of maximal faces. Remember that this is exactly the regularity divided by, I can do exactly the same thing here. The same K here, D minus 0 inside D, in the notation before, of E of V1 up to VD without 0. This is exactly because of the regularity that every, let's think that we are in dimension 3, say. Every triangle is contained in exactly the same number of pyramids. Or every triangle of type 1 up to D is contained in exactly the same number of pyramids. Minus the product of AI divided by VI, I go now from 1 up to D. And because of the fact that this and this collapse, I'm getting exactly the discrepancy of this part. Okay. This is kind of a trivial lemma, but it plays a role, so I wanted to show it before the break and now. And let's take a break, and after the break, I want to make sure that we finish the data proof, because I don't want. I mean, it's really easy. It's just that the notation are a little bit confusing. So we'll finish it after. So let's keep this and keep this, and then well, this. I already had the lemma 0, which basically was kind of a tautology, but it was important to notice this tautology because it was because of the regularity. Here we really used the regularity in an essential way. Now I want to say the following, that I want to define another graph. Okay, so that we will do the following. I want to say that the, okay, let's call it lemma 1. The discrepancy of X tau of sets A0, A1 up to AD. Eventually, that's what we want to. This is really what we want to bound, is at most the discrepancy of the following graph. Let's look at the graph that we called before BI. So remember what is BI? Was the graph such that on one side of it we have VI, on the other side of it we have the walls of all the walls of type without I, and some edges between them according to the definition. You know, if together they create, they form a chamber. So I take this discrepancy of BI of the set. So I take here 0. Now A0 is a subset of Vi, so that's fine. Now I have to put on the other side, now I'm talking about discrepancy in a bipartite graph. In a bipartite graph, I have only two sets that should be put. On one side, I have to put a set in Vi. In the other side, I have to put a subset of this. The subset of this will be all the walls of A1 up to AD. So I take the walls of type A1 up to AD, namely all the walls without 0, but such that the vertices inside them are in A1 up to AD. And I ask what the discrepancy in the bipartite graph, but this is not the end, plus AI1 divided by A0 divided by V1 by V0 times the discrepancy in X of the set A1 up to AD. Now, I wrote the lemma in this way with the 0 because I didn't want to make too many notations, but we are going to use it also with different indexes, and you will understand that this is exactly the same thing. Okay, we'll come to it.
Should BI be 0?
What?
Should BI be 0 or?
Where is VI?
Discrepancy.
Hey, you're right. VI is oh, yeah, right. So this is VC. Yeah. That's exactly. Yeah. I said that I'm doing it for 0, but I will use it also for the others. But let's put it just for the zeros. So I really should write V0. Okay. So I can bound the full discrepancy. It's kind of an inductive process. I can bound the full discrepancy by a discrepancy of this bipartite graph plus something which is less than 1. Okay, and you'll see that if somebody wants to be very, very precise, I'm really giving up on information here. If it's really small set, it's much less than 1. Times the discrepancy of that set, okay? And then we'll continue this by induction after that. But let's prove first this lemma, and the proof is just a computation, but let's be careful. So what is this? By definition, this is the size of E A0, A1 up to AD divided by the full, by E of V0, V1 up to VD, right? The total number of edges, maximum faces, minus the product of J goes, or I goes, from 0 up to D of AI divided by VI. And this can be written as E of A0 against E of A1 up to AD. Now this is edges in B0. You see, the number of chambers A0, A1 up to AD is the same as the number of edges between A0 to walls. This is the set of walls of type A1 up to AD, right? in the bipartite graph B0. Do you see that this is the same number? Divided by this number. So we just call it maybe E of x. I don't want, this is just E of x, like the total number of edges of x. When I say edges, I mean maximal edges, right? Like maximal chambers. Okay? E of x. Minus AI0 divided by VI0 times, let's give this a name. I will call this E prime minus E prime divided by E of D minus 0. Now, you don't even have to understand what I write it, because I will do this minus plus exactly the same thing. So I'm certainly allowed to do it. Even if I sometimes don't put the E of D minus 0. Minus, so I we'll come back to that in a second, but I subtract something and I add something. Minus, no, I'm sorry. Yeah, I do this like that. Plus this, in brackets here, minus the product I goes from 1 up to D of AI divided by VI.
Here you wrote AI0.
Maybe I'll bring a color to see that there is some brackets here which goes on this. So this is minus plus, I just added something. And this is minus what I had before.
You wrote there AI0, but I think you
It should be A0, so not A0, it's A0. I mean, in my notebook I wrote it with general notation AI, but it doesn't matter, but I decided, I will, you are intelligent enough to do it for zero, you understand that it works for everyone. Okay, so this is the same thing. And let's just to understand what we put here. We put here E prime. E prime is the number of walls lying on the set A1 up to 80. On the sets A1 up to 80. These are the codimension 1 faces whose vertices are on this. Okay, so now you can see that this is at most. This is at most. And now I can like triangle inequality. I can write this minus this. But now let's think. What I'm claiming that what is written here is exactly the discrepancy in the graph B0. In the graph B0, such that on one side I have EA0, and on the other side I have something. Okay? Because what should I do? Because this is exactly what is written here. What is written here is written, think about this term and this term only. Right? Then on one side you have a 0, on the other side you have all the walls, the set of all the walls, which lying on the sets A1 up to 80. This is a set of vertices in the bipartite graph, B0 on the right hand side. And I have to divide it by the total number of edges. The total number of edges in B0 is exactly as the total number of chambers in the complex, because every chamber uniquely associated with an edge in this bipartite graph, such that on one side you have the vertex of color 0, and on the other side you have a wall without 0. Right? All chambers are like that. And every chamber is expressed like that in a unique way, as a one vertex of color 0 and one wall without a 0, which are connected between them. So this is exactly the discrepancy here. And now, plus A0 over V0 times what? Now we have to understand, so this is exactly what I promised you here, plus A0. Now I claim that what is written here inside the brackets is exactly the definition of the discrepancy, that's clear, of A1 up to AD. Without A0, right, we define discrepancy of, I take a subset of types, right? And in each one of them, this time the subset is only the colors between 1 to D, without a 0 color. And we have E prime is exactly the faces with colors 1 up to D, such that the points are in A1 up to AD. Right? Divided by the total number of this type, the total number of these types of vertices, of faces is this one, minus the expected value of them, which is exactly this one. So this is exactly the discrepancy in X of A1 up to AD without A0. Okay? There. And now let's prove the result. And now I have to bound oh no, I shouldn't. I made a mistake. There's something in train. Okay. So finally, now, so we finished. This was proved. This was a proof of lemma 1, and now we can prove the proposition. So what we have to bound? We have to bound the discrepancy we have to bound the discrepancy of A1, of A0 up to AD. For all subset A0 up to AD, this discrepancy of X star. Right? Okay, well, we start with the discrepancy with capital D of X star. This is equal to the maximum on things like that. On discrepancy of A0 up to AD. So we have to bound this kind of thing. Okay, so let's see by dilemma. This is at most the discrepancy of inside B0 of A0 against something. Against A1 up to AD plus A0 over V0, the discrepancy inside X of the sets A1 up to AD. Right? This is lemma 1. Now, this is at most the discrepancy of B0. But the discrepancy of B0 is at most this lambda normalized. So this is at most the lambda normalized of B0. Now plus 1, the discrepancy of this. But I can do now exactly the same trick. It doesn't matter, because you remember, okay, I'll do it slowly. This is by lemma 1. Now I'm going to use lemma 0. Lemma 0 told me that this discrepancy is the same as the discrepancy of x of the full set V0, A1 up to AD. You remember? That's what we did before the break. The discrepancy of x1 up to xd is the discrepancy of B0, A1 up to AD. Okay, are you with me? Now, there was nothing special. There was nothing special here when I prove lemma 1. I prove it for V0, for the first. But there was nothing special about color 0. This is the same as in all the other colors, right? So this is the same. So this will be at most. Now I'm using lemma 1, but the essence of lemma 1, right? Not formally lemma 1, because I'm using it for A1. So this is the same. Now, first of all, lambda normalized of B0 plus, now the new thing will be lambda normalized of B1 plus A1 divided by B1, the discrepancy of V0 A2 up to AD. Okay? Because lemma 1 told me that the discrepancy of A0 up to A1 up to AD is at most the discrepancy in the bipartite graph of B0, but now I'm using it on the bipartite graph of B1, plus A1 over V1, the discrepancy if I eliminate the set A1. Right? Are you with me, right? So, okay, and this is at most lambda normalized B0 plus lambda normalized B1 plus, now this I can replace by 1, plus, right, this is 1, is at most 1, and this discrepancy, I can do it by the same argument. It's the discrepancy of V0, V1, A2 up to AD. This is again using lemma 0. And now you can see the rest, right? Now, and now I will go, and now I will eliminate A2, etc., etc. And then it will be eventually the sum. I think, by the way, we don't need the last one, if I'm not mistaken. It's really even lambda normalized of BI, because I think if we go from 0 even up to B minus 1, what will be left eventually? It will be the discrepancy what it will be eventually. It will be the discrepancy of when I stay here with only 2, and then I eliminate this one. So this is exactly the number of this one against all the other. I don't know, I'm not sure. Maybe we don't. I don't care. I don't know, if you want to think about it, maybe we don't need the last one. We can choose who will be the last one. maybe says something that some of the last one, which means that if you have a good estimate somehow on d out of the d plus 1, maybe that's enough. I don't know. Anyway, this is at most d plus 1, the maximum of these lambda normalized of this bi, and the propositions.
How do you get the,
Yeah, questions?
why is the discrepancy go away at the end?
Why what?
I mean, at the end of the discrepancy, V0, V1 up to VD, is that obviously?
I can't hear you.
Why?
Follow the pattern and the discrepancy, V0 up to VD.
V0, A2, AD.
So after you do all these by induction, you get discrepancy V0 up to VD plus this side of the normalizer, right?
Yeah, but you're right. I'm getting a bad, but the discrepancy of this is 0. You're right. You see, the discrepancy, you're right, I have to say that. The discrepancy eventually, you see, I'm getting the discrepancy of V0, V1, V2, up to VD. I'm filling all of them, right? But what is this? By definition, this is the number of edges between them divided by the total number of edges, which is exactly the same thing. It's 1 divided by 1, minus the product of VI divided by VI. So it's 1 minus 1 is equal to 0. Good. Should be said. Okay, now let me give you an exercise which I don't know to solve. But I believe, and I think it would be useful. I don't know if maybe I don't know. I don't want to start the subject now because this will be in this semester. We will mainly work with the simplicial complexes, and I'm kind of going into the next topic will be buildings and quotients of building, with the idea to show that if you take quotients of the Boas-Titz building associated with some p-adic groups, then you are getting simplicial complexes with very small discrepancy, namely they are very good expanders in this sense, or if you want, they have a very strong mixing lemma. And this mixing lemma will enable us to evaluate various combinatorial properties of them, like chromatic number, like independent set, and also the overlapping, the geometric overlapping that I told you about, if you still remember, in the first lecture. In fact, that will be maybe the most important application, that they satisfy this geometric overlapping property. And the way, and this will come up by using the results of Pach, which I don't think I mentioned. I could stop here and explain why this is important, but I prefer maybe not to do it because I decided, this is a joint course with Gil Kalai, and he will teach the second semester, and he will take more, he will teach this Pach theorem, etc. And then we will come to use the application. So meanwhile, you should take my word, and I think you get a feeling that these kind of mixing properties are strong properties. But still, I want to relate it somehow to the spherical complexes. And the exercise I want to give you is a challenge, because I don't know. I showed you how to compute various bipartite graph associated with the spherical complex. Remember, we took dimension 1 against dimension 2, 2 against 3, etc. We didn't even do this in a very general. But the right one, which we really need, exercise, challenging exercise. I And maybe it's not known, I mean, I don't know, but I think there are tools to do it. Maybe nobody was interested in doing this before. But I think it will have some application is take X to be S, this spherical building S, D, Q. I don't know, S and Q, dimension and Q. You can talk about the general case, but if you want, why don't we can start with the small numbers. I think it's starting to be interesting, maybe with n equal 4, 5, something like that. And then evaluate this lambda of BI. Or if you want the lambda normalized. The lambda normalized is not, I mean, the lambda normalized is really the second largest eigenvalue of BI divided by the first eigenvalue. The first eigenvalue is not that difficult to compute. It needs some work, but it's not difficult because let's see what I mean by that. So what it will be really BI? BI it will be spaces. So on one side, so the BI will be bipartite graph. This is a bipartite biregular graph, as we talked today. On one side, you remember we have the spaces of dimension I, but on the other side, we are going to have walls without I. All the walls without I, which mean flags, which is really flags without dimension I subspaces. So on one side we'll have, I don't know, some W's of dimension I. On the other side we are going to have something which will be a U1 inside U2, inside UI minus 1, inside UI plus 1, etc. up to inside UN minus 1. Right? These are the flags without anything of dimension I. So it's not difficult to see what are the degrees, at least from one side. The degree from this side is clearly Q plus 1. Because if I have a flag like that, which is almost complete except of dimension I, but UI minus 1 and UI plus 1 are already fixed. So the number of ways to complete it inside here is exactly Q plus 1. So the degree on this side is going to be Q plus 1. The number of walls can be computed. I mean, it's an exercise. You know, it's the number of subspaces of dimension 1, and then the number of subspaces of dimension 2 containing it, and then up to here is no problem. Yeah, like this is a standard exercise that we understand. Now we have to jump in this quotient. We have to jump and go to count the number of I look at the quotient, which is of dimension n minus I minus 1, and I compute the number of subspaces of dimension 2 instead of 1, so I jump over there, and from there on I continue as before. So we can evaluate. This is going to be a very long number, a very large number, and here we are going to have a relatively small number, the number of all, well, not so small, by the way. If I is in the middle, like if I is more or less n over 2, then that's a fairly large number. So I'm getting here a bipartite graph, and then if I know, and then I can compute also the degree from here, either directly, just thinking about it, if you fix W of dimension I, how many flags you have which start below it and go up to W, and then start after W and go up to the very end. Well, that's not, I mean, all this is a simple linear algebra that I'm sure you can fix. What is less clear to me is how to evaluate the eigenvalues here, because the usual trick that I showed you in those cases when I computed, then we took the adjacency operator of this bipartite graph and we took the square of it. And some of the square of it is associated always to path of length 2. And it was, in all the cases where I computed, it was possible to pass from a space of, from one space to another in a path of length 2. If you remember the J, the matrix J appeared. It was A square equal to the something, the identity, plus J minus something with some constant. And this was the trick. Now, it's not true in general. If I take a subspace of dimension 5, I take two subspaces of dimension 5, then I cannot find a wall connecting one of them. Right? They're not in two steps. They can have, somehow there might be a larger distance. And I'm not sure really how to do it. I mean, it's probably possible, maybe it's known. I'm sure it's somehow in the literature. I don't know if it's elementary or needs some representation theory, but I think it will be useful to know, because if we will have good bounds, I will be happy for a bound which will tell that for a fixed n, and q going to infinity, to show that this lambda normalized of bi for all of them, or if you want the maximum of them, is going to 0. I'm sure it's true, but I don't know to prove it. And I think a result like that will have various combinatorial applications. So let me encourage you to take the challenge. Okay. Next time, buildings. We'll go to the building of a periodic. Now, how many of you knows what are periodic numbers? Or let's ask, who doesn't know what are periodic numbers? Okay, so maybe a little quick review, but do me a favor and take a look in the book. Or even go to the internet, write periodic numbers, and read the one page on the basic definition somewhere that you will feel comfortable, because we will need it. We will work over the so-called local field. Local field, basically, there are two basic examples. It's either the periodic number, the so-called QP, or FQ. You take a finite field, and you take the Laurent power series over the finite field with, so these are all the Laurent power series, the formal power series over FQ with things like that, sigma, AI, e to the I star in some m up to infinity with m, any integer. It can be also negative. And this is a field. You can multiply them, etc. These are the two types of local field that we will work with, so you should be kind of comfortable with working with them, what are periodic integers, etc.